So, the last class we took a look at oblique shock waves now in a two dimensional flow, and whenever there is a turn of the flow towards itself, into itself, it causes compression and oblique shock form. The way to analyze oblique shocks is to look at components of velocity parallel and perpendicular to the oblique shock, and parallel to the oblique shock velocity remains the same across the oblique shock, while the perpendicular components are related by normal shock relation. So, that was the straightforward understanding of oblique shocks. If you understand that, it is very easy to analyze oblique shocks. And the other main feature is the way the oblique shock behaves to changes in flow deflection, which is given by m theta beta relationship. So, there are attached oblique shocks and detached oblique shocks or detached shocks. Attached shocks are when the angle of deflection is less than the maximum angle for which a attached shock can be solved, and those can be solved using the m theta beta relation. So, we saw all this in the previous class. The counterpart to that is when the flow turns happens away from the mainstream, then how do we analyze these features or flow features. And then we saw that you get expansion waves or expansion fan. So, how do we analyze expansion fans? So, for this we begin initially with the flow undergoing a gradual turn towards itself, and understand what happens as the oblique shock become weak. Okay, so as oblique shocks become weaker and weaker, then they turn to be very close to Mach waves that we had discussed very early on, and there the entropy changes across the oblique shock become almost 0. This you can show. This is what we had discussed earlier, which is the oblique shock when there is a sharp turn to theta and an oblique shock is formed. Now, if you take the limits of these oblique shock, at the maximum limit the oblique shock can have an angle 90 degree to the flow, that is the particular form, that is the normal shock. The flow deflection in this case is 0, that is absolutely normal. The second one is when the shock can go to very weak values, the minimum that it can go towards is a Mach wave. So, across a Mach wave also the flow deflection is almost negligible, so you can take it to be 0, and the pressure ratio is 1. So, the two limits for an oblique shock are at the lower limit it tends to be a Mach wave, and at the very strong limit it goes to a normal shock. So, both are in the normal oblique shock system itself. Okay. So, now instead of considering such a sharp turn, the total turn through angle theta can be done through a subsequent or sort of set of small changes, small angles. At each small turn you have a oblique shock. Okay. So, you have an oblique shock, but now since the initial turn is very small, the delta theta or small change is small, the shock wave strength is also small. Okay. So, the same turn theta is accomplished by many waves. You can keep increasing the number of waves and make the turn more gradual. So, this is a very gradual turn, smooth turn across to the angle theta. Okay. So, now let us consider this particular problem, a gradual turn. So, across each small turn there is an incremental change in pressure. Okay. So, that is how it happens. Now, consider that so there is a entropy change across the oblique shock, and the entropy change is the same as that for a normal shock for normal component. Okay, so that is what is written over here, delta S for the oblique shock, and this is for a normal shock, and here if you substitute for m1 you substitute m and 1, then you get it for an oblique shock. And in the normal shock discussions we also saw what happens when the strength of normal shock goes weaker and weaker, it becomes very small. It is called the weak shock limit, and in weak shock limit we saw that the entropy goes extremely small. Okay, it is extremely small, and the way it goes is to the power cube. Okay, so to power cube, so m and 1 square minus 1 the whole power cube. This was discussed in the context of normal shocks. Now in the context in oblique shocks, if you look at it, now the same angle theta is divided into small turns of very small angle. You consider many such turns, then across each very weak oblique shock the change in entropy is given by this term, basically this term, or where this is now delta theta. So delta S goes approximately as delta theta cube. Of course, so you make theta smaller and smaller, delta S is going to be smaller and smaller. Now what is delta theta? So if you divide this turn into n number of turns, then theta is delta theta is theta by n. So you get you can substitute that there, and you get that the change in entropy delta S essentially goes as theta cube by n square, okay, for a gradual turn. Now we apply the state condition that n goes to infinity. If you want to make it a smooth and continuous turn, as n goes to infinity delta S goes to 0, or you are getting an isentropic flow. So a gradual turn very close to the wall, if you look at it, it is an isentropic flow, and each wave is actually a very weak oblique shock. In the limit of weak oblique shock, it is nothing but a Mach wave. Okay, so you have several Mach waves. So this gives us the idea how to go ahead and analyze the expansion waves, because you cannot have an expansion shock. So in when you have to turn the flow away from the wall, the flow has to accelerate, but pressure, density and temperature will decrease, but that cannot be accomplished by a sharp discontinuity like the oblique shock. But this small analysis on gradual turns gives you an idea that if the flow happens to change gradually, then the flow is essentially isentropic, and then there is no problem with violation of second law of thermodynamics and so on, and therefore you can turn the shock or turn the flow away from itself, and this is accomplished. So always the flow turn away from the flow, that always happens by means of a gradual turn. So a sharp discontinuity of this sense is not possible. This is an expansion shock is not possible, because always you should have positive change in entropy. So what is possible is actually a gradual turn or gradual change in flow. So this is the gradual turn away from the flow, and the flow remains isentropic, and it is bound by Mach waves. Now these are Mach waves. Okay, so this is starting Mach wave nu1, this is at the end nu2, and since they are related, nu is sine inverse 1 by m. So Mach number is increasing across the turn, therefore you have nu2 is always less than nu1. Now in the limit what you can what is considered is this gradual turn. This corner can be sharp, so it can be a sharp corner, but the turn actually happens very gradually in as a series of waves, a series of Mach waves do the turn to the flow. Only at this corner you have a where all the points are starting. So that is this kind of an analysis is done by Prandtl and Meyer. So this is known as Prandtl-Meyer function or Prandtl-Meyer angle. How do we do this analysis? So we again draw the velocity triangles across one single expansion wave, across a wave, a certain wave, very similar to the analysis that was done earlier for the oblique shock. We look at the components of these velocities. So before, that is the upstream of the expansion wave, you have the velocity v, that is drawn over here, corresponding to this v or Mach number m. You have a Mach wave. Okay, so this is the Mach wave at an angle nu. So this is angle nu. Now with respect to this Mach wave, you draw all the others. So as the flow goes through the Mach wave, it undergoes a very small change in angle, that is d nu. Okay, and a small change in velocity v plus dv, but again the concepts of oblique shock remain, that is the tangential component is remaining conserved. So Vt is the same. What is Vt? Vt is v cos nu. So that is what is mu. V cos mu is the same as v plus dv, cos mu plus d nu. So mu plus d nu, that is what is written over here, conservation of the tangential component. Now you know that d nu is very small, is almost tending to 0, it is very small. So cos d nu is 1 and sin d nu tends to d nu. Expand cos nu plus d nu using trigonometric relations and you get cos mu cos d nu, sin nu and sin d nu, and use these relations. So you get v plus dv cos mu minus dv sin nu. Okay, so you get these terms, and from here there is a v cos mu term here and a v cos mu term that comes over here. So they cancel each other. Okay, and you have this term dv d nu sin mu. Both are small changes. So this is a very high order term. The small changes, if you multiply together, it becomes very small. So this term is also neglected. So if you then write down this equation, what you get is d nu is equal to cot mu dv by v. Okay, so this is the equation. So what is cot mu? You can draw the angles. So this is what is mu. Mu is sine inverse 1 by m. So this side is m square minus 1. So cot mu is square root of m square minus 1. So that is given here. So now this particular expression relates d nu, which is known as nu is the Prandtl-Meyer function, to the change in velocity dv by v. Now the idea is, can we express dv by v in terms of Mach number dm? Can this be done? We can do it because v is Mach number multiplied by speed of sound, and that is v is square root of gamma r multiplied by square root of t. These are constants. If you take logarithm and differentiate, dv by v is dm by m plus half dt by t. So that is what is given here. Okay. dm by m plus half dt by t. Now can we express dt by t in terms of dm by m? We know that this flow is isentropic. So for an isentropic flow, T0 by T is 1 plus gamma minus 1 by 2 m square. This we know from first principles from the earlier classes, and again you can use the same kind of logarithm differentiation. T naught is constant, okay, constant, T naught is constant. So this is essentially dt naught by T naught minus dt by t is equal to gamma minus 1 2m and half they go off. So m dm by 1 plus gamma minus 1 by 2 m square. Okay, so you get dt by t, this is 0. So dt by t is minus gamma minus 1. So you can put this relationship into there, and so you get dm by m minus half, and then do the algebraic manipulations. You get dv by v is 1 plus gamma minus 1 by 2 m square dm by m, and this is substituted, and so you get expression for the Prandtl-Meyer function explicitly in terms of gamma and m. This is a calorically perfect gas, gamma is constant. This can be integrated, and this is the integration for. So this is the Prandtl-Meyer angle. Once you integrate this, it is the Prandtl-Meyer angle. Here we take so of course you will have a constant. The constant is taken that nu equal to 0 at Mach number equal to 1. So when Mach number is 1, the Prandtl-Meyer angle is 0. So once that is taken, you get this relationship. Okay, so this is given in any charts, you can get this, and this is a Prandtl-Meyer angle. Now how is Prandtl-Meyer angle related to the change in angle during a flow turn? So the flow turns by an angle delta theta. So before this flow turn, the Prandtl-Meyer angle is nu 1, and this is nu 2, and nu 2 is nu 1 plus delta theta. During a flow turn away from the upstream flow, Prandtl-Meyer angle increases, so that is what you have to consider. During a turn, a gradual turn, so a compression turn, the Prandtl-Meyer angle decreases, so it takes a negative sign, minus delta theta. So you should always remember these. So for gradual turns, for both compression and expansion, you can use the Prandtl-Meyer analysis, and you can relate the downstream and upstream conditions. Okay, so the relationship is nu 2 is nu 1 minus delta theta for compression, and nu 2 is nu 1 plus delta theta for expansion or turn away from. So what we saw this is here is the analysis of expansion waves, and we saw the way to look at this problem is starting from a smooth turn and show that at the weak limit of oblique shocks you get Mach waves, and entropy change is negligible there. So you can accomplish the same turn by a series of Mach waves, which is what is done in case of which is the case of an expansion fan, where the flow turns away from the incoming flow. Then the Mach number increases, pressure, temperature, density decrease. How to calculate pressure, temperature, density? Very simple, it is an isentropic flow, use isentropic relations. So from using those concepts, we came to the Prandtl-Meyer analysis and the Prandtl-Meyer relation that relates the Prandtl-Meyer angle, and these are the relations for a smooth compression or an expansion. So, now we will apply these in certain flow scenarios. We will start with we can couple shocks and expansions and look at how pressures behave over bodies. And then the other point is what happens when these shocks they are present in the flow and they interact with a wall or they interact with virtual surfaces in the flow which have constant pressures. What happens then? So, these are the questions we will answer in the coming classes.